All right, good, good. Okay, let's do another one here. We won't get through it. I mean, this one will go faster though. Now that we've been through one of these things, we can charge through this one a little. Okay, this is we'll just look at one more of these rational functions. Did we do one? Okay, so we got two more. These are pretty quick ones though, but I want to go through both of these because there's some stuff on these that we still haven't talked about. So what about this one? So we know that the domain, we have to exclude the values -1 and 1, right? We already did that. We know this is an odd function because the top is odd and the bottom is even, right? Or you can just do the test for symmetry and you'll prove to yourself that it's odd. Okay, we took limits here too, right? Remember, we reviewed our limits of rational functions, and in this case, because the denominator is a higher degree polynomial than the numerator, the limit as x approaches plus or minus infinity is 0. Okay, another way of looking at that, though, and this is the way, honestly, I prefer to look at it, is I just look at if they're rational functions, you can just replace the rational function. If we're looking at the tails of the function, we're approaching positive or negative infinity, the behavior is going to be the same as if I only focus on the dominant leading terms, right? So in other words, the limit of this rational function as x approaches plus or minus infinity is exactly the same as the limit of the ratio of only the leading terms, right? To me, that just seems like a simpler way to think about it. You don't have to remember any rules that way. And then if I simplify this, the ratio of the leading term simplifies to 3 over x, and as x goes to infinity, that obviously goes to 0, doesn't it? Right? Okay, so we get a horizontal asymptote then. That just tells us our horizontal asymptote is y equals 0, is the x-axis. Okay? All right, so now what? We need to do some derivatives then. What about vertical asymptotes? Are there any vertical asymptotes here? Caleb, any vertical asymptotes for this function?
I think Are negative 1 and 1 both requests?
They are, right, because those are unique zeros of the denominator, right?
Yes.
Okay, so we know that we have vertical asymptotes at x equals plus or minus 1. Okay, so we got lots of asymptotes. Now we need to do some calculus, so let's differentiate. And we've just got to use quotient rule, right? So we get x squared minus 1 times the derivative of the top, which is just 3, minus high d low. So 3x times the derivative of the bottom is just 2x divided by the bottom squared. Okay, and we can simplify that. Anything I can do there that's handy? Well, yeah, there is. So if I distribute the 3, I get 3x squared minus 3 minus 6x squared. So I end up with minus 3x squared minus 3. Is that right? I think it is. Yeah. Over x squared minus 1 squared. And if I factor out a negative 3 on the top, I get negative 3 times x squared plus 1 divided by x squared minus 1 squared. Is that right? Everybody see any mistakes there? Give me a thumbs up if that looks right to you. Okay, so are there any zeros for the first derivative then? Any zeros for the first derivative? No? Agreed? Top is never 0. Are there any critical numbers where the first derivative is undefined? Okay, what are the critical numbers where the first derivative is undefined? Type them in chat if there are any. We're just looking for all the critical numbers of the first derivative, right? So where it's undefined or equal to 0. Okay, so negative 1 and 1, I've seen negative 1 and 1, I'm seeing a 1. Okay, and I get that because that's where the second derivative, where the denominator is 0, right? Okay, but keep in mind, critical numbers can only exist where the function is defined, right? So are those actually critical numbers? No, function's not defined there. So in the domain of the function, there are no critical numbers. So we have no extrema on this thing, okay? Second derivative. So how about if we just go from here? We'll use that version right there. Okay, so if I just differentiate using the quotient rule, I'm going to get x squared minus 1 squared times the derivative of the top, which is negative 6x, minus the top times the derivative of the bottom. Now that's chain rule, right? I've got hand squared, so I get 2 hand to the 1 minus the derivative of hand is 2x divided by the bottom squared. Well, x squared minus 1 squared squared is just to the 4th power. Okay, now can we factor out some common factors? Looks like it, doesn't it? Look, I've got like bases on the top. I can factor out an x squared minus 1 from the top. And I can factor out, how about if I factor out I could factor out a 2x also. How about a negative 2x? What's that leaving me with then? So here's my minus sign. What am I left with from the first term? If I take out an x² minus 1, I've taken one of those away. I've got one left. Factored out a negative 2x, leaving me with a positive 3. So I've got 3 times the quantity x² minus 1. Everybody good with that from the first term? Okay, this is where it'd be nice to give me, if you can, flip your camera on and give me a thumbs up when you're ready, when you're good to hear, so I know that. Okay, I'm getting lots of thumbs up. Okay, I'm gonna move on then. So I factored this out of the second term. Now what's that giving me? So if I factor out a negative 2x, so that's gone, and I'll go ahead and just do this because I took that negative out, right? So now what am I left with? 2 times 3x², so I've got a 6x² that I'm subtracting, and I'm going to distribute that negative, and I'm subtracting a 6. All over x² minus 1 to the 4th, but I can cancel a factor vertically, like so. Oops. And now I get what on the top? So I get negative 2x times, what happens if I combine all this stuff? 3x² minus 6x² is negative 3x². And here I'm getting minus 3 minus 6. So minus 9, is that right? I think that's right. Man, I feel like I think that's right. So why didn't I do this? Make all those positive. Okay, give me a thumbs up if you agree with me on that one. Andy, what did I do wrong?
Well, I just have a question. Can you factor a 6 out of the x² minus 6, and then you can factor it out again and cancel, make it like a squared on the bottom?
Oh, I see what you're saying. Factor a 6 out of that. Yeah, what did I do? So something's goofy there, huh? Oh, no, I can't, because look, if I factor no, I'd have to, I can't, I see what you're saying, but I can't because look, this is a negative 6x² minus 6. If I factor a negative 6 out of this, I'm going to get an x² plus 1 from this guy. Okay, makes sense? Okay, so now I need thumbs up, thumbs down. Are we okay with that, or did I do it right? Everybody agree? You see any problems? Okay, so zeros, there it looks, we get no zeros of the denominator that are in the domain, but there is a 0 of the numerator, isn't there? I get x equals 0 is a 0 of the second derivative. Everybody agree? Okay, so let's make our table. Okay, so we had Positive and -1 were our vertical asymptotes, right? Those are values where the function is undefined. So these are vertical asymptotes. We can just put a line down there. So we know those are vertical asymptotes. We had a 0 of the second derivative at 0. So what do we need to do here? And we know we have a horizontal asymptote. Let's do this too. We can write it this way. So if we take a limit as the function as x approaches -infinity, y was 0, and the limit as x approaches +infinity is 0. So we can see we get horizontal asymptotes there. Okay. And if I start to graph this thing, those asymptotes really help with the graph. Oh, what's going on here? Oh, never mind. Okay, I guess I have to go to the next page to graph this thing. There's my horizontal asymptote. There's a vertical asymptote. There's a vertical asymptote, right? A lot of asymptotes. What do we need to do? Where do we need to pick some test points? What do you think, Andy? Where should I pick some test points?
Can you pick them on the either side of 0?
Yeah, okay, so I got to go, and I have to pick them between the vertical asymptotes and 0, don't I? So something like, for example, we could pick like -1/2 and 1/2. And I'm just evaluating the second derivative there. So at +1/2, what do we get? We get, let's do it this way, f double prime of 1/2 equals, on the top we're going to get positive times positive divided by 1/2 squared is 1/4 minus 1. That's negative cubed is negative, right? So positive over negative, it's giving us negative, isn't it? We get a negative second derivative there. What about at -1/2? If I did the same thing at -1/2, the bottom is going to stay negative, isn't it? That factor is always positive, but this one becomes negative. So it's going to look like that. So it does change concavity at 0. Okay, so we know then, let's go ahead and plug 0 into our function. What do we get if I evaluate this at 0? Well, I just get 0. So at the point 0, 0, I have an inflection point coupled with my vertical asymptotes. I know what this graph looks like, right? How would I graph that? If I know I've got a point at 0, 0, and it was, what was the concavity? It was negative to the right and positive to the left. What does this thing have to look like there then? If it's concave down to the right, up to the left, only one thing it can do, right? Doesn't it have to do? Doesn't it have to do that? Everybody see that? Because it has to stick to those asymptotes, right? Give me a thumbs up if that makes sense. You see how much those asymptotes help us? They really help. Now, what about out here on the other sides? So there's only two things it could possibly do, right? Either this function is going to be doing this, because there are no extrema, right? So either it's doing that or it's doing that. Same thing over here. We have to just figure out which one is it. So we could work we could work in any column we want to, or any row we want to here, whichever one seems easiest for the functions. What if we look at the first derivative? The first derivative, the top is always negative. Agreed. And the bottom is always positive because it's being squared. So the first derivative is always negative. What does the graph have to be doing then? Right? It's got to be, if it's always negative, it has to be decreasing. Let's look at this part over here. If it's always decreasing and it has to adhere to these two asymptotes, doesn't it have to be doing that? Everybody agree? Has to, right? Okay, on the other side, if it's always negative and it's got to stick to this horizontal asymptote and that vertical one, it's got to do that, right? Now, we know that for a variety of reasons, though, too, because we already knew that it has odd symmetry. So we know this thing's also got rotational symmetry about the origin. So whatever the right half of this function looks like to the right of x equals 0, if I spin this thing 180 degrees, it's got to line up with the left side. So that works, doesn't it? Okay, we could have done this in the second derivative row of our table. If we went down to the second derivative, we know that if I were to pick a test point down here, for example, we'll just pick like 10 or something, right? So if it's a negative 10. If I pick 10, the sign of the second derivative at 10 is going to be positive times positive divided by positive, so it's positive. Well, there it is. If it's going to be stick to these asymptotes and be concave up, that's the only place it could be. By the odd symmetry, then it's got to look like this over here, right? Or if I wanted to pick a test point, I could have done that too. It all works. If I plug negative 10 in, I'm going to get negative times positive over negative. Yeah, hold it. No, getting negative. Yeah, I'm getting negative times positive over positive. So it's negative, right? Makes sense. So it's concave down. Okay? How about that? All that stuff is contained in that table. That's pretty cool. You get all that information in that table. Okay? Thumbs up, thumbs down. How we do it? Give me 1 to 5 on that one. Okay?